Light is all around us, illuminating our world, powering life and revealing the vastness of the cosmos. Yet behind its familiar glow lies a profound mystery. What is light made of? This simple question bridges everyday experience and the deepest ideas in quantum physics. It invites us to explore how something as ordinary as light leads to the discovery of the photon, the tiny, indivisible packet of energy that changed our understanding of reality itself. A photon is the most fundamental building block of light, the smallest possible packet or quantum of electromagnetic energy that can exist. It is the indivisible unit from which all forms of light and electromagnetic radiation are made, whether it be the glow of a candle, the invisible waves carrying radio signals, or the intense radiation from a distant star. Unlike matter particles such as electrons or protons, photons have no rest mass, no electric charge, and cannot be broken down into smaller components. Each photon represents a single pulse of the electromagnetic field, carrying energy that depends directly on its frequency. Higher frequency photons such as X-rays or gamma rays carry more energy, while lower frequency photons such as radio waves carry less. This simplicity makes photons extraordinary. They are universal messengers that move through the fabric of space at the ultimate speed limit of the cosmos, the speed of light. Every flash, every reflection, and every colour we perceive is the collective result of countless photons interacting with matter. They define light not as a continuous glow, but as a stream of discrete quanta, each one a fundamental carrier of electromagnetic energy. And yet before the birth of quantum theory, light was not thought to be made of particles at all, a belief that led to one of the greatest scientific revolutions in history. Before the dawn of quantum theory, scientists viewed light purely through the lens of classical physics. To them, light was a continuous wave, a rhythmic oscillation of electric and magnetic fields spreading smoothly through space, much like ripples on the surface of a pond. This wave model elegantly explained many of light's behaviours, such as reflection, refraction, diffraction, and interference. The brilliant patterns seen when light passes through slits or around obstacles seem to confirm that light had no particulate nature at all. Thinkers like James Clerk Maxwell solidified this view in the 19th century by uniting electricity and magnetism into a single framework, showing mathematically that light was an electromagnetic wave travelling at a finite, constant speed. For decades, this picture reigned unchallenged. In laboratories and theory alike, light was thought to be infinitely divisible and continuous. No smallest piece, no discrete packet, just smooth, undulating fields. To suggest otherwise seemed absurd, even unscientific, because waves were, by their very nature, spread out and continuous. Yet as experiments grew more precise at the turn of the 20th century, strange results began to appear, results that classical physics could not explain. These inconsistencies cracked open the door to a new and unsettling idea. Perhaps light was not purely a wave after all. The idea that light could behave both as a wave and as a particle stands as one of the most revolutionary and mind-bending discoveries in all of science. Known as wave-particle duality, this concept shattered the clear boundaries that classical physics once drew between waves and particles. Before quantum mechanics, scientists categorized the natural world neatly. Waves were continuous, spread out disturbances like sound or ripples in water, while particles were discrete, localized bits of matter such as atoms or grains of sand. Light had always fit comfortably in the wave category, until experiments began to show that it sometimes acted like a stream of particles too. The first hints came from the behavior of light itself. When light passes through two narrow slits, it produces an interference pattern, bright and dark bands that can only be explained if light behaves as a wave, with crests and troughs overlapping and cancelling each other. This is the famous double-slit experiment, first performed by Thomas Young in the early 1800s. The interference pattern clearly demonstrated that light could spread out and interfere, proving its wave nature beyond doubt. For over a century, this was considered final evidence that light was not particulate. But the dawn of the 20th century brought experiments that defied this comforting picture. When light was shone onto certain metals, it ejected electrons from their surfaces in a process called the photoelectric effect. According to classical wave theory, shining a brighter light, regardless of colour, should eject electrons with greater energy. But in reality, no electrons were ejected at all unless the light's frequency was above a certain threshold, no matter how bright the light was. This strange behaviour made no sense if light was merely a wave, yet it fit perfectly if light consisted of discrete packets of energy, photons, each carrying a specific quantum of energy proportional to its frequency. This revelation, first explained by Albert Einstein in 1905, changed physics forever. It showed that light sometimes behaves as though it is made of particles, not continuous waves. Each photon hits the metal surface like a tiny bullet, transferring its energy to an electron and knocking it free if and only if it has enough energy. This explanation didn't just solve a puzzle, it revealed that light could exist in two seemingly contradictory forms, depending on how it was observed. Subsequent experiments deepened the mystery. When light was measured in situations emphasizing interference, it behaved like a wave, spreading out and overlapping with itself. But when detected as discrete impacts, say by a sensitive photo detector, it revealed its particle side, arriving as the individual quanta. Even more astonishingly, when scientists performed the double-slit experiment with the individual photons fired one at a time, the interference pattern still appeared after many photons had passed through, as if each photon interfered with itself. This suggested that a single photon does not simply travel through one slit or the other, but somehow explores both paths simultaneously until a measurement forces it to choose. This bizarre behaviour became a cornerstone of quantum mechanics, the theory that governs the microscopic realm. In quantum terms, a photon doesn't have a definite nature until it is measured. Its behaviour, wave-like or particle-like, depends entirely on the kind of experiment we perform. In a sense, the photon embodies both possibilities at once, existing in a superposition of states that only collapse into a definite outcome when we observe it. This is not just a limitation of our instruments, it reflects the fundamental indeterminacy of nature itself. Wave-particle duality blurs the line between energy and matter as well. Later discoveries showed that all particles, even those we once thought of as purely solid bits of matter, like electrons or protons, also display wave-like properties. In other words, everything in the universe has both wave and particle characteristics. What we call particles are really localized excitations of quantum fields that can interfere and diffract just like light. Thus, light is not unique in its duality. It simply revealed the rule first. The implications of this duality are profound. It challenges our most basic intuitions about what it means for something to be a particle or a wave. The photon isn't one or the other. It is something deeper, something that transcends classical categories. Depending on the context, we may describe it as a wave to explain interference or as a particle to explain energy transfer. But neither picture alone captures its full reality. The truth lies in the mathematics of quantum theory, where light is described by a wave function, a probability amplitude that encodes all possible outcomes. In practical terms, this duality explains countless phenomena. Lasers rely on the coherent wave nature of photons, while solar panels depend on their particle nature. Even the screens we use to watch light-based images, such as in cameras and computers, depend on photons behaving as particles that deliver discrete packets of energy to sensors. Each technological triumph of the modern world, from quantum communication to spectroscopy, owes its existence to our acceptance of light's dual identity. Wave-particle duality forces us to think differently about what reality means. Light, once thought to be simple and continuous, turns out to be a manifestation of a probabilistic quantum world. When we see sunlight glinting off water or a beam passing through a prism, We are witnessing countless photons behaving collectively as a wave. But when a photon triggers a sensor in a camera or liberates an electron in a solar cell, it reveals its individual particle-like nature. In short, light's true nature is not something we can pin down in one form. It is a hybrid born of the quantum domain, a bridge between waves and particles, continuity and discreteness. The photon defies classical logic, reminding us that the universe operates on principles that challenge intuition but reveal breathtaking harmony at its most fundamental level. At the dawn of the 20th century, physics stood on the brink of a crisis. Classical theories, which had long described the universe as smooth, continuous, and predictable, began to fail in the face of new experimental data. One of the most pressing mysteries concerned blackbody radiation, the light emitted by a perfectly absorbing object as it is heated. According to classical physics, as an object's temperature increased, it should emit light with intensities that climbed infinitely at higher frequencies. This prediction, known as the ultraviolet catastrophe, was absurd. It suggested that even a small hot object would radiate an infinite amount of energy. Experiments clearly showed otherwise, and the elegant equations of classical physics could not explain why. It was in confronting this problem that Max Planck, a German physicist, made a revolutionary proposal in 1900 that would forever change the foundations of science. Planck was searching for a mathematical formula that could fit the experimental data describing how objects emitted radiation at different wavelengths and temperatures. In a desperate move, more an act of mathematical necessity than philosophical conviction, he introduced a radical idea. Light could not radiate energy continuously. Instead, it must emit or absorb energy in discrete chunks, which he called quanta. Each quantum of energy he proposed was proportional to the light's frequency, expressed in the simple relation E equals h nu, where E is the energy of the quantum, nu is its frequency, and h is a new constant, now known as Planck's constant. This idea was astonishing in its simplicity, yet revolutionary in its implications. Planck suggested that energy came in indivisible packets, much like coins rather than a continuous stream of currency. The higher the frequency of the light, the more energetic each quantum would be. Low-frequency radiation, such as radio waves or infrared light, carried smaller energy quanta, while high-frequency light, such as ultraviolet or X-rays, carried larger ones. This concept was utterly foreign to classical physics, where energy was assumed to vary smoothly, without any smallest unit. Initially, Planck did not fully grasp the physical meaning of his own discovery. He saw quantization as a mere mathematical trick to make his equations work, not as a statement about the true nature of light or energy. Yet this modest adjustment solved the ultraviolet catastrophe perfectly, matching experimental results with uncanny precision. Without realizing it, Planck had laid the groundwork for quantum theory, the most successful and far-reaching scientific framework in history. In the years that followed, other scientists began to explore the implications of Planck's quantization. If energy is emitted and absorbed in discrete quanta, then light itself must consist of these individual packets. It could no longer be viewed as a continuous wave of energy flowing smoothly through space. It must be composed of distinct, countable bursts. This was a profound departure from centuries of thought stretching back to Newton and Huygens. The smooth classical picture of light as a continuous wave was giving way to a deeper, grainier reality, where even the flow of energy was quantized. The concept of energy quantization not only explained blackbody radiation, but also hinted at a hidden structure in nature itself. It suggested that the universe is not infinitely divisible, that even at the smallest scales, there exists a fundamental granularity to energy, time, and matter. The world was not an endlessly smooth continuum. It was built from indivisible units governed by discrete transitions. Planck's constant h became one of the most fundamental numbers in physics, defining the very scale of quantum effects. It tells us how grainy the universe is at its smallest level. In everyday life, this granularity is invisible because h is so small, approximately 6.626 times 10 to the negative 34th joule seconds. But at the atomic and subatomic scales, where photons, electrons, and other particles operate, it dominates reality. There, the discreteness of energy cannot be ignored. It determines how atoms emit light, how molecules form bonds, and how matter interacts with radiation. The idea that energy comes in quanta soon gained experimental support. When light interacts with matter, it does so not in continuous streams but through sudden jumps. Atoms absorb or emit energy only in precise amounts corresponding to the energy difference between allowed quantum states. This is why elements produce distinct spectral lines, unique fingerprints of colour when heated or excited. Each line represents photons of a specific energy released as electrons fall from one energy level to another. This observation confirmed Planck's hypothesis. Nature operates in quantized steps, not continuous flows. The concept of quantization opened an entirely new view of the universe. It bridged the macroscopic world of thermodynamics with the microscopic world of atomic behaviour. It introduced the possibility that light, and perhaps everything else, was fundamentally granular, a collection of tiny, indivisible units acting in harmony. But while Planck had provided the mathematical framework, it was Albert Einstein who just a few years later gave this quantization a concrete physical interpretation. Einstein boldly declared that light itself was composed of individual quanta, later called photons, and that these photons carried energy exactly in the way Planck had described. This idea, radical and controversial at the time, would not only explain the photoelectric effect but also launch the full development of quantum mechanics. Thus, Planck's discovery of energy quantization was more than a solution to a mathematical problem. It was the spark that ignited a scientific revolution. It marked the moment humanity first glimpsed the quantum world, where the seemingly continuous fabric of energy and matter breaks down into discrete, indivisible units. It taught us that light, the most familiar thing in our experience, hides a secret structure, one that reveals the universe is not smooth, but quantized at its core. The turning point that's transformed Max Planck's abstract mathematical idea into a physical reality came with Albert Einstein's explanation of the photoelectric effect in 1905. This was one of the defining moments in modern physics, an insight so profound that it not only earned Einstein the Nobel Prize, but also redefined the very nature of light. It was here that the photon, the quantum of light, stepped from theory into the tangible world of experimental proof. The photoelectric effect had puzzled scientists for years. When light shines onto the surface of certain metals, it can eject electrons from that surface, creating an electric current. This phenomenon was well known in the late 19th century and was even being harnessed in primitive light sensors. However, the details of how it occurred refused to fit the predictions of classical physics. According to the wave theory of light, the energy delivered to a metal surface should depend only on the intensity of the light, the brightness or amplitude of its waves, not on its colour or frequency. In that framework, a brighter light carrying more total energy should always be able to eject electrons if it shines long enough, no matter what colour it is. But that wasn't what experiments showed. Researchers such as Heinrich Hertz and later Philipp Lenard observed that no electrons were emitted from the metal unless the light's frequency was above a certain threshold, no matter how intense the illumination was. For example, even a dim ultraviolet light could liberate electrons from a metal surface, while an extremely bright red light, though vastly more intense, could not. Even more astonishing, when light above the threshold frequency did cause electrons to be ejected, the emission happened instantaneously. There was no measurable delay, as one might expect if electrons were gradually accumulating energy from a continuous wave. Something deeply counterintuitive was happening, something that the continuous wave theory of light could not possibly explain. Einstein approached this mystery through the radical lens opened by Planck's quantum hypothesis. If light's energy came not in a continuous flow, but in discrete quanta, then each quantum or photon would carry a specific amount of energy determined by its frequency, following the formula E equals h nu. In other words, blue or ultraviolet light has photons with higher energy than red or infrared light because it oscillates at a higher frequency. Einstein proposed that these individual photons strike the electrons in the metal surface one at a time, transferring their energy in a single, all-or-nothing collision. If the energy of a photon exceeds the binding energy, the amount required to liberate an electron from the surface, it knocks that electron free. If the photon's energy is below that threshold, no electron can be ejected, regardless of how bright the light is, because adding up weaker photons cannot substitute for one that meets the required energy per quantum. This explanation perfectly matched the experimental observations and made several striking predictions that could be tested directly. First, the kinetic energy of the emitted electron should increase linearly with the frequency of the light, not with its intensity. Second, increasing the intensity of the light should increase the number of electrons emitted, but not their individual energies. Third, there should be an abrupt cut-off frequency below which no electrons are released at all. Every one of these predictions was confirmed with remarkable precision, providing overwhelming evidence that Einstein's photon hypothesis was correct. Einstein's insight did far more than explain an odd experiment. It redefined the meaning of light itself. For centuries, light had been described as a wave, spreading through space continuously, diffracting and interfering in predictable patterns. Now, Einstein showed that light also behaves as a collection of particles, each carrying a precise quantum of energy. This dual nature of light, both continuous and discrete, was the first clear demonstration of wave-particle duality, and it would go on to become one of the cornerstones of quantum mechanics. The implications of Einstein's theory were staggering. It suggested that electromagnetic radiation, even the soft glow of a candle or the hum of a radio wave, is composed of countless individual quanta, each a photon, each with its own identity. Light was not merely a field vibrating through space. It was also a stream of energetic messengers capable of exerting direct, particle-like impacts. This shift in understanding forced scientists to abandon the notion that light could be fully described as a classical wave. Instead, light had to be treated as a quantum phenomenon, a field that manifests as discrete packets when interacting with matter. Einstein's explanation also illuminated the behavior of matter at its smallest scales. When a photon strikes a metal surface, it transfers its energy instantaneously to an electron. If that energy exceeds the metal's work function, the energy required to escape its atomic bonds, the electron is emitted. The excess energy appears as the electron's kinetic energy, its speed as it leaves the surface. The beauty of Einstein's formula lies in its clarity. Kinetic energy of electron equals h nu minus phi. Here, F represents the work function of the metal, and h nu is the energy of the incoming photon. This simple equation connects the abstract concept of quantized light energy directly to a measurable real-world effect. It allowed scientists to determine Planck's constant experimentally, and confirm the discrete nature of light's energy with mathematical precision. Einstein's work not only validated Planck's hypothesis, but also provided the first direct evidence that energy quantization was not just a theoretical artifact, it was a physical truth. It bridged the world of pure theory and tangible experiment, transforming quantum physics from speculation into a discipline grounded in observation. Moreover, it opened a new era of scientific exploration, the recognition that all interactions between light and matter occur in discrete quantized exchanges. This understanding of the photoelectric effect would go on to influence technologies that shape modern life. From solar panels converting sunlight into electricity, to photodetectors in cameras, fiber optic systems, and quantum communication networks. Every one of these advancements relies on the principle that photons transfer energy in individual quanta. In a single stroke, Einstein had shown that light is not just a wave washing over matter. It is a storm of tiny energetic quanta, each capable of changing the state of matter upon contact. He had taken Planck's mysterious constant and revealed its profound meaning. Energy in the universe is not continuous but quantized. This insight laid the groundwork for the quantum revolution that would soon follow, giving rise to new theories of atoms, fields, and the very structure of reality itself. Light, once thought to be a smooth, ethereal wave, was now understood to arrive in sharp quantized pulses, each one a photon, a tiny carrier of energy from one place to another. Through the photoelectric effect, Einstein had transformed the nature of light from something intangible and continuous into something measurable and discrete. The photon had officially entered the lexicon of physics, not merely as a concept, but as a fundamental constituent of the universe. When we ask the question, what are photons made of, it may seem straightforward. After all, we're used to thinking of things as being composed of smaller parts. Atoms are made of protons, neutrons, and electrons. Protons and neutrons, in turn, are made of quarks. Even molecules, planets, and stars can be broken down into more fundamental constituents. But when it comes to the photon, this line of questioning reaches a profound stopping point. Photons are not made of anything, they are not composites or collections of smaller entities. Instead, they are elementary particles, meaning that to the best of our current understanding, they represent one of the most basic building blocks of reality itself. In modern physics, the term elementary particle refers to something that cannot be divided or reduced into more fundamental parts. These are the indivisible ingredients from which all matter and forces in the universe arise. The standard model of particle physics, our most successful framework for describing the fundamental constituents of the cosmos, lists photons among this elite category. Alongside particles like electrons, neutrinos, and quarks, photons occupy a unique position as the force carriers of the electromagnetic interaction. They are the quanta, the smallest possible units of the electromagnetic field. The misconception that photons might have an inner structure arises from our human intuition, shaped by experiences with macroscopic objects. We instinctively imagine light as something tangible, tiny bullets, grains, or beads of energy flying through space. But this image, while convenient, is misleading. A photon is not a little ball or packet of matter. It is a quantized excitation of the electromagnetic field. In simpler terms, is a ripple in that field, a burst of oscillating energy that propagates through space. It doesn't have internal components or substructure. There are no smaller pieces inside it. No core, no shell, and no charge distribution. To describe this more rigorously, consider what it means for a particle to have structure. Composite particles, such as protons, exhibit measurable internal complexity. They can be probed at high energies, revealing constituent parts that interact within them, quarks held together by gluons. When experimental physicists perform high-energy scattering experiments, smashing particles together at near-light speeds, they can observe how internal components influence the outcomes. The photon, however, shows no such internal response. No matter how high the energy used to probe it, the photon behaves as an indivisible point-like entity, consistent with having zero spatial extent and no substructure. Another defining feature of the photon's simplicity is that it has no rest mass and no electric charge. Because of this, it doesn't decay into smaller particles, nor does it carry the properties that would allow an internal configuration to exist. Its entire identity is determined by just a few fundamental parameters. Its energy, E, frequency, Nu, wavelength of tau lambda, momentum, P, and polarization or spin state. These characteristics are not things that come from inside the photon, they are inherent properties of its very existence. They describe how the photon behaves, not what it's made of. In quantum field theory, the deepest framework we currently have for describing the universe, fields, not particles, are the primary ingredients of reality. The electromagnetic field is one of these fundamental fields filling all of space. A photon arises whenever this field is excited in a particular way. Thus, to ask, what is a photon made of, is somewhat like asking, what is a wave made of in the ocean? The wave isn't made of anything separate. It is a motion or disturbance of the water itself. Likewise, a photon is not a substance or object made of smaller parts. It is a localized excitation of the electromagnetic field. This field-based perspective clarifies why the photon behaves as both a particle and a wave. As an excitation, it travels through space as a wave, spreading and interfering like ripples in water. But when it interacts with matter, say by striking an electron or being absorbed by an atom, it delivers its energy in discrete quantized amounts, just as if it were a particle. These two faces of the same entity, the continuous field and the discrete quantum, are not contradictory but complementary descriptions of one and the same physical phenomenon. It's also worth emphasizing that the photon's indivisibility has been tested to extraordinary precision. Particle accelerators and high-energy physics experiments, such as those conducted at CERN and other facilities, have probed the photon across energy scales billions of times higher than those of ordinary visible light. If photons had any internal structure, even the slightest trace, it would have revealed itself through subtle deviations in their behavior, shifts in how they scatter, interact, or propagate. Yet every experiment to date has confirmed that the photon behaves as a point-like, structureless elementary entity. In this way, the photon stands apart from most of the particles we encounter in everyday matter. While electrons are also elementary, protons, neutrons, and atomic nuclei are not. Photons, being pure quanta of the electromagnetic field, occupy a different category altogether. They are bosons, meaning they obey quantum statistics that allow multiple photons to exist in the same state. This is what makes coherent light, such as in lasers, possible. Countless photons occupying a single quantum mode, moving in perfect synchrony. Yet even in such collective behavior, each photon remains indivisible. Its energy cannot be split into fractions. The question what are photons made of also leads to a deeper philosophical point about the nature of fundamental reality. It reveals the limits of reductionism, the idea that everything can be explained by breaking it into smaller and smaller pieces. At some level, the process of division stops, and we encounter the truly fundamental entities from which everything else emerges. Photons are part of that foundation. They are not made of something else, rather, everything else that interacts electromagnetically is influenced by them. So when we speak of photons, we are not talking about miniature balls of light or objects composed of parts. We are describing pure energy quanta, indivisible excitations that mediate one of nature's four fundamental forces, the electromagnetic force. They are as close to the elementary as our current understanding allows. In essence, asking what a photon is made of is like asking what a number is made of. It doesn't have components, it simply is. Thus, the photon represents one of the ultimate building blocks of reality. Not a thing built from smaller things, but a manifestation of nature's fundamental fields. It is both the simplest and one of the most profound entities known to science. Massless, chargeless, indivisible, yet responsible for everything from the warmth of sunlight on your skin to the glow of distant galaxies. One of the most remarkable aspects of the photon, and one that beautifully unites the wave and particle views of light, is the direct relationship between its energy and its frequency. This connection, first expressed by Max Planck and later expanded by Einstein, tells us that photon's energy is not arbitrary or continuous, but precisely defined by how rapidly its electromagnetic field oscillates. In simple terms, the faster the vibration of the electromagnetic wave, the more energetic each photon is. This relationship is expressed by one of the most elegant and fundamental equations in all of physics, E equals h nu. Here, E represents the energy of a single photon. H is Planck's constant, a fundamental number that sets the scale of quantum phenomena, and nu, the Greek letter nu, represents the frequency of the electromagnetic wave. Frequency measures how many oscillations or cycles occur in 1 second, and its unit is the hertz, Hz. This simple equation tells us that the energy carried by light is not determined by how bright it is, but by the colour, or more precisely, by the frequency of the light itself. To understand why this matters, imagine the electromagnetic field as a continuous ocean of oscillations. Each photon corresponds to one quantum of that field, and the rate at which the field oscillates, its frequency, dictates the amount of energy contained in that quantum. A red photon, whose frequency is relatively low, carries less energy than a blue photon, which oscillates much faster. Push the frequency higher still, and you reach ultraviolet light, X-rays and gamma rays, each photon increasingly more energetic, capable of penetrating materials or even altering atomic structures. Conversely, lower frequencies such as microwaves and radio waves correspond to photons with extremely low energies too weak to affect atoms individually. This relationship between frequency and energy helps explain an enormous range of physical phenomena. For instance, when you heat a piece of metal, it first glows red, then orange, then white as its temperature rises. The increase in temperature causes the atoms in the metal to vibrate more rapidly, emitting photons of higher and higher frequency, and therefore higher energy. This is why a red-hot object is cooler than a white-hot one. The photons being emitted have less energy per quantum. Similarly, in astronomy, the colour of a star reveals its temperature. Bluer stars are hotter because they emit more high-frequency, high-energy photons, while redder stars are cooler, radiating lower-frequency photons. The equation E equals h nu also clarifies a subtle but essential distinction between a light beam's brightness and its energy per photon. Brightness, or intensity, depends on how many photons are present, not how energetic each one is. A bright red light contains more photons per second than a dim blue light, but each red photon still carries less energy than each blue one. This difference is critical in understanding phenomena like the photoelectric effect, where the colour of light, not its brightness, determines whether electrons can be ejected from a metal surface. A flood of low-energy photons cannot accomplish what a few high-energy photons can because each photon acts independently when interacting with matter. From a deeper quantum perspective, the photon's energy-frequency relationship emerges naturally from the structure of the electromagnetic field itself. In quantum field theory, every field can be thought of as a set of oscillators, each vibrating at specific frequencies. The photon corresponds to a single quantum of vibration within the electromagnetic field. The faster the oscillation, higher the frequency, the greater the energy of that quantum excitation. This means that a photon is not an arbitrary chunk of energy. It is the minimal possible amount of energy associated with a specific oscillation mode of the field. The consequences of this quantization are profound. For example, in spectroscopy, the study of how atoms and molecules absorb and emit light, each element has a distinct set of energy levels. When an atom absorbs a photon, it can only do so if the photon's energy exactly matches the difference between two of those levels. Because the photon's energy is fixed by its frequency, this means only specific frequencies can be absorbed or emitted, giving rise to the unique spectral fingerprints of different elements. When you see the bright red colour of a neon sign or the specific orange hue of sodium streetlights, you are witnessing photons of specific frequencies corresponding to these exact energy transitions. In addition, this relationship defines the photon's momentum, since in quantum mechanics, energy and momentum are intrinsically linked. Although photons have no rest mass, their energy and frequency imply that they still carry momentum, given by P equals E over C equals nu over C, where C is the speed of light. This momentum is what allows photons to exert pressure, known as radiation pressure, and transfer force, even in the vacuum of space. For instance, sunlight can push on the tails of comets or power experimental spacecraft equipped with solar sails, a tangible demonstration of light's ability to carry momentum despite its lack of mass. Moreover, the relationship between frequency and energy defines the vast electromagnetic spectrum. On one end, we find long-wavelength, low-frequency radiation, radio, microwaves, and infrared, with photons carrying minimal energy per quantum. On the other, we encounter ultraviolet light, X-rays and gamma rays, whose photons are immensely energetic, capable of ionizing atoms and altering the structure of DNA. The visible portion of the spectrum, the narrow band that human eyes can perceive, occupies only a tiny sliver in between, from roughly 400 terahertz, red, to 750 terahertz, violet. Every color we see corresponds to photons vibrating at distinct frequencies, each delivering a precise quantum of energy to the photoreceptors in our eyes. Understanding this connection between energy and frequency also deepens our appreciation for the universality of physical laws. Whether a photon originates in a distant quasar or a household light bulb, its energy is always determined by the same rule: E equals h nu. There is no exception, no context in which this relationship changes. Planck's constant acts as the bridge linking the continuous world of electromagnetic waves with the discrete quantized realm of photons. It is one of nature's most fundamental constants, the fingerprint of the quantum universe itself. In essence, the photon's energy-frequency relationship reveals that light's color is not merely a perceptual quality, but a direct measure of quantum energy. When you look at a rainbow, you're literally seeing energy arranged in order, each hue corresponding to photons vibrating at different rates, from low-energy reds to high-energy violets. Every glimmer, reflection, or shimmer is the universe's way of translating oscillations of the electromagnetic field into packets of quantized energy. Thus, the photon's energy is not a mysterious attribute added onto it. It is its defining characteristic. The faster the oscillation, the greater the energy it carries. The slower the oscillation, the gentler its touch. Through this relationship, nature encodes its most profound balance. Light as both rhythm and particle, continuous in motion but discrete in energy. In the modern understanding of physics, photons are not tiny glowing marbles racing through space, nor are they minuscule balls of energy floating in a vacuum. Instead, they are excitations, temporary disturbances or ripples, within a fundamental entity known as the electromagnetic field. This shift in perspective is one of the greatest conceptual revolutions in science. It transforms light from being something that travels through space to something that is a property of space itself. To understand this, we must begin with the concept of a field. In physics, a field is a continuous entity that fills all of space and can carry energy, momentum, and information. Fields are not made of particles, rather, particles are the quantized manifestations of these fields. For example, the gravitational field defines how masses interact, the electron field gives rise to electrons, and the electromagnetic field governs the behavior of electric and magnetic forces. These fields are not confined to specific locations, they exist everywhere, even in what we call a vacuum. Empty space is not truly empty, it is alive with underlying fields, constantly fluctuating at the quantum level. The electromagnetic field, specifically, is a dynamic fabric woven from electric and magnetic components that oscillate and sustain each other. When this field is undisturbed, it sits quietly, holding potential energy but not expressing it. When disturbed, say by an accelerating electric charge, it begins to ripple, producing oscillations that propagate outward. In classical physics, those ripples are the electromagnetic waves described by Maxwell's equations. In quantum physics, however, we learn that those same ripples are not continuous but quantized. Each discrete unit of oscillation corresponds to a photon, a single quantum of the electromagnetic field. This means that photons are not objects within the field, they are the field's quantized excitations. Think of plucking a guitar string. The vibration that travels along it is not a physical bead or ball, it is a disturbance of the string itself. Similarly, when an atom emits light, it is actually creating a localized disturbance, a quantum tremor in the electromagnetic field, which we detect as a photon. When the photon is absorbed, the disturbance ends, and the energy it carried is transferred to another system, such as an electron in an atom. In this picture, photons are not flying projectiles that move through space like bullets. They are wave-like ripples in a universal field that extend across space and time. These ripples can interact with matter in discrete particle-like ways, depositing or absorbing precise amounts of energy, but their essence remains that of a field excitation, not a miniature object. The quantization simply means that the electromagnetic field cannot possess arbitrary amounts of energy. It can only contain energy in multiples of h and nu, where nu is the frequency of oscillation. This field-based understanding resolves many of the paradoxes that puzzled earlier scientists. For example, how can light interfere with itself if it's made of particles? In the field view, this is no mystery at all, because the photon is not a localized object, but an extended field excitation that can take multiple paths simultaneously, producing interference patterns just as waves do. Likewise, how can a photon deliver energy all at once to a single electron if it's also spread out as a wave? The answer is that when the field excitation interacts with matter, the interaction occurs at one specific quantum point, collapsing the energy transfer to a single event, even though the probability of that interaction was distributed over space. In this framework, quantum field theory, QFT, the most successful theoretical structure in modern physics, provides the mathematical foundation for describing photons as excitations of the electromagnetic field. In QFT, each type of particle in the universe corresponds to its own field. Electrons are excitations of the electron field, quarks are excitations of the quark field, and so on. The photon, therefore, is the quantum of the electromagnetic field, just as a sound wave is a vibration of air. This model replaces the outdated particle versus wave debate entirely, revealing that both descriptions are partial views of the same underlying phenomenon. What's fascinating is that even in the absence of real photons, the electromagnetic field never truly rests. Quantum mechanics dictates that it constantly fluctuates due to zero-point energy, producing transient virtual photons that pop in and out of existence, mediating electromagnetic forces between charged particles. These virtual photons are not directly observable, yet their effects are measurable. For example, in the Casimir effect, where two metal plates placed close together in a vacuum experience a slight attractive force due to quantum fluctuations of the electromagnetic field between them. This subtle phenomenon is one of the many ways the field's restless nature manifests itself, even in what appears to be empty space. Another powerful implication of viewing photons as field excitations is that it unifies light and electromagnetism. Before quantum theory, light and electromagnetic forces were treated as distinct phenomena, but in the field picture, they are inseparable aspects of the same entity. The light that illuminates a room, the radio waves carrying information, and the electric forces holding atoms together are all expressions of the same field behaving in different ways. When charges accelerate, they create oscillations in this field, photons that radiate outward, carrying energy and momentum across space. This perspective also clarifies why photons travel at a constant speed. The speed of light, c, because they are massless excitations of the electromagnetic field, photons are not objects being pushed through space. They are self-sustaining ripples that propagate at the natural speed determined by the properties of the field itself. Just as waves on the surface of water have a characteristic speed depending on the medium, the electromagnetic field has its own propagation speed, c, which is the same for all photons, regardless of their energy or frequency. When we speak of photons being emitted or absorbed, what we're really describing are transitions in the electromagnetic field's energy state. When an atom's electron drops from a higher energy level to a lower one, the electromagnetic field gains a quantum of energy, the photon. When another atom absorbs that photon, it excites the field back to its lower state while transferring that energy to the atom's electron. These processes are continuous at the level of the field but discrete in the transfer of energy, perfectly embodying quantum behavior. This field excitation view of photons has also been confirmed experimentally in countless ways. For example, phenomena like spontaneous emission, stimulated emission, the basis of lasers, and quantum entanglement of light all rely on the idea that photons are quantized field disturbances. The field model not only predicts these effects, but also explains their probabilistic nature. Photons do not have definite positions until interactions occur, and their behavior arises from the underlying field's wave function rather than any hidden trajectory. In short, photons are not things in space, they are patterns of space itself, ripples in the electromagnetic fabric that permeates the universe. Every beam of light, every spark, every reflection is a fleeting disturbance in this omnipresent field, a momentary excitation that carries energy, momentum, and information from one place to another before fading back into the quiet structure of the vacuum. Thus, the photon is not a particle in the classical sense, but a quantum event, a manifestation of the field's quantized nature. It represents one of nature's most elegant truths. The universe is built not from objects that move through space, but from fields that ripple, vibrate, and exchange energy in discrete quanta. Photons are the shimmering pulses of that eternal motion, the heartbeat of the electromagnetic field itself. In modern physics, quantum field theory, QFT, stands as the ultimate framework for understanding what photons truly are. It goes far beyond the early ideas of light as a wave or as a stream of particles, offering a unified and profoundly elegant picture. Photons are quanta, tiny, indivisible excitations of the electromagnetic field itself. They are not objects flying through space like miniature bullets, nor are they mere undulations of energy detached from matter. Instead, they are the quantized manifestations of an underlying continuous field that fills the entire universe. Every instance of light being emitted, transmitted, or absorbed corresponds to a change, a discrete step, in the energy of this field. To grasp this, it helps to appreciate what quantum field theory represents. QFT is not simply an extension of quantum mechanics, it is a redefinition of what we mean by particle and field. In classical physics, fields, like the electromagnetic field, are smooth, continuous entities that can vibrate and propagate as waves. Particles, by contrast, are localized, tangible units of matter with a definite mass and position. These two ideas were once thought to be incompatible, but QFT bridges them, revealing that fields are the true fundamental entities of nature, and what we call particles are merely quantized vibrations or excitations of those fields. In other words, matter and energy are not separate substances, they are two expressions of the same underlying quantum fields behaving in different ways. In the case of light, the electromagnetic field is the fundamental entity. According to QFT, this field can exist in different states of excitation. When it is in its lowest energy configuration, we call that the vacuum state, representing space with no real photons present. Though even this vacuum is not truly empty, as it teems with virtual fluctuations. When energy is added to the field, say, when an atom releases light, a localized excitation occurs. That excitation is what we call a photon. It is a discrete, indivisible packet of energy corresponding to one quantum of the electromagnetic field. This concept reshapes how we understand emission and absorption. When an atom's electron drops from a higher to a lower energy level, it doesn't eject a pre-existing particle of light. It triggers a change in the electromagnetic field, causing the field to transition from one quantum state to another. The result of this transition is the creation of a photon. Conversely, when an atom absorbs a photon, the field loses that quantum of energy as the atom's electron jumps to a higher energy state. Thus, emission and absorption are not collisions between separate entities, but quantum transitions within an all-encompassing field. One of QFT's most profound insights is that photons are not localized objects moving through space independently of the field. The field is the photon, and the photon is a state of the field. When we detect a photon, say, when it strikes a sensor in a camera, what we're detecting is the field interacting with matter at a single quantum point, transferring its discrete energy hν in one indivisible act. This is why photons are always emitted and absorbed as whole units. The field cannot release or take up half a quantum of energy. Quantization imposes a natural granularity on what was once thought to be continuous. Quantum field theory also brings mathematical precision to these ideas. In this framework, every field has corresponding operators that can create or destroy quanta. For the electromagnetic field, these are the photon creation and annihilation operators. When light is emitted, the creation operator acts on the vacuum state to produce a one-photon state. When light is absorbed, the annihilation operator removes that quantum from the field. This process doesn't describe a photon traveling like a ball, it describes how the field's quantum state evolves through interactions. The mathematics of QFT thus captures both the particle-like and wave-like behavior of photons in a single seamless formalism. This framework is extraordinarily successful, providing predictions that match experiments with astonishing accuracy. For example, quantum electrodynamics, QED, the branch of QFT dealing specifically with the electromagnetic field and its interaction with charged particles, has produced results verified to better than 1 part in a billion. It explains how photons mediate the electromagnetic force, how electrons scatter light, and how subtle effects like the Lamb shift or the anomalous magnetic moment of the electron arise from quantum fluctuations. Every one of these predictions hinges on the idea that photons are quanta of the field, appearing or disappearing as the field interacts with matter. What makes QFT so powerful is that it unifies all of nature's particles and forces under one conceptual roof. Each type of particle, electrons, quarks, neutrinos, and even the elusive Higgs boson, corresponds to its own field. Matter particles are excitations of matter fields, while force carriers like photons, gluons, and W and Z bosons are excitations of force fields. Photons in particular are the quanta of the electromagnetic field, the mediator of all electromagnetic interactions. Whenever an electron feels an electric or magnetic force, that interaction is mathematically described as an exchange of photons, some real, some virtual within QFT. The field perspective also dissolves the need to think of photons as having definite paths through space. Instead, the electromagnetic field extends everywhere, and its excitations evolve according to the probabilities governed by the quantum wave function. When we perform an experiment to detect a photon, whether in a double-slit interference setup or a photodetector array, we're not catching a little particle that took one path or another. We're measuring a single event that collapses the field's probability distribution into a definite outcome. Between emission and detection, the photon does not travel along a classical trajectory. It exists as a superposition of possibilities, a cloud of potential interactions encoded in the field's quantum state. Perhaps one of the most profound consequences of QFT's interpretation is that it reframes our understanding of empty space. The vacuum is not nothingness. It is a seething sea of quantum fields in their lowest energy states, constantly fluctuating due to the uncertainty principle. Even in the absence of real photons, virtual photons continuously pop in and out of existence, mediating forces and giving rise to observable effects. The electromagnetic field, in its quietest state, is still dynamic, restless, and full of potential. A photon, then, is not an isolated entity emerging from nothing. It is a brief, organized ripple in this omnipresent field, born when energy is exchanged between matter and radiation. This field-based vision of photons also explains their fundamental properties. Their masslessness arises naturally from the gauge symmetry of the electromagnetic field, meaning they must always move at the speed of light. Their spin, a quantum form of angular momentum, is an intrinsic property of the field structure, dictating how photons can be. Polarized. Their ability to interfere, diffract, and exhibit entanglement are direct consequences of their origin as field excitations rather than classical particles. In this light, quantum field theory reveals the photon as more than a unit of energy. It is a bridge between the discrete and the continuous, between the local and the universal. Each photon marks a moment when the electromagnetic field's seamless continuity expresses itself in quantized form, making the invisible fabric of the universe perceptible to our instruments and senses. Thus, in the QFT picture, light is not something that moves through space as a collection of particles. It is a state of the electromagnetic field itself. A photon is the smallest possible unit of that state, the tiniest packet of field energy that can be created or absorbed. Whenever a light bulb glows, a laser fires, or a star burns, what we're witnessing are not streams of tiny objects racing through emptiness, but the electromagnetic field changing its configuration, rippling, quantizing, and transferring energy in perfect accordance with quantum laws. At first glance, it seems impossible that something with no mass could exert a push. In classical physics, momentum, the measure of an object's motion, is directly tied to mass. A heavy object moving fast has high momentum. A massless entity, by that logic, should have none at all. Yet photons, which are massless quanta of the electromagnetic field, do carry momentum. They can transfer that momentum to matter, exerting a measurable force known as radiation pressure. This surprising property is one of the most profound illustrations of how the laws of quantum and relativistic physics differ from our everyday intuitions. The explanation for this lies in Einstein's broader view of energy and momentum, which emerged from the theory of relativity. In that framework, mass is not the only source of momentum. Energy itself contributes to it. Einstein's famous equation, E=mc², is often misinterpreted as applying only to objects with mass, but it actually expresses a deeper truth, that mass and energy are interchangeable forms of the same underlying quantity. For massless particles like photons, energy and momentum are related differently through the equation P=E/c. Here, P is the momentum of the photon, E is its energy, and c is the speed of light. Since a photon's energy is also given by E equals h in nu, its momentum can be expressed as P equals h nu divided by c equals h divided by lambda, where lambda is the wavelength of the light. This simple yet profound relationship shows that every photon, no matter how faint or low in energy, carries a definite and quantifiable momentum determined solely by its wavelength. This means that when light interacts with matter, when photons strike a surface or absorbed, reflected, or scattered, they transfer momentum to that material. Each photon's impact imparts an infinitesimal kick, but because light consists of an immense number of photons, the cumulative effect becomes measurable. This phenomenon is what we call radiation pressure. Radiation pressure can be observed in many contexts, from the laboratory to the cosmos. In everyday experiments, scientists can measure it using extremely sensitive instruments such as torsion balancers or micro-cantilevers. When a beam of light shines on a small reflective surface, the photons striking and bouncing off it impart momentum, producing a tiny but real force. If the light is absorbed instead of reflected, the momentum transfer still occurs, though the magnitude is smaller because the photon's direction changes less dramatically. This principle has even been used to cool and trap atoms using lasers. By tuning the light to interact in specific ways, physicists can manipulate atomic motion with extraordinary precision, a technique that has given rise to laser cooling and optical tweezers. In the vastness of space, radiation pressure plays a far grander role. Stars, for instance, continuously emit enormous quantities of photons. Each photon streaming outward from a star's surface carries momentum, and when these photons strike dust, gas, or planetary atmospheres, they exert a gentle outward force. Over time, this pressure can shape cosmic environments. It can push gas and dust away from hot young stars, sculpting the dramatic nebula formation seen in astronomical images. In massive stars nearing the end of their lives, radiation pressure can become so intense that it counteracts gravitational collapse, regulating how the star evolves and how it sheds its outer layers. Perhaps one of the most vivid examples of photon momentum in action is the solar sail, a spacecraft propulsion concept that harnesses radiation pressure as a means of travel. A solar sail consists of a large, ultra-thin reflective sheet that captures the momentum of sunlight. Each photon that strikes the sail transfers a tiny push, and though the force is minuscule, it is continuous. Over time, these countless small impulses accumulate, gradually accelerating the spacecraft. Unlike traditional engines that consume fuel, a solar sail relies solely on the steady stream of photons from the Sun. Missions such as Japan's Icaros, interplanetary kitecraft accelerated by radiation of the Sun, and the Planetary Society's light sail. Two have demonstrated that this concept works. Photons, despite being massless, can propel an object through the vacuum of space. The ability of photons to carry momentum also underpins many technological and natural phenomena on Earth. For example, in laser ablation, powerful laser pulses vaporize material by transferring both energy and momentum to a target surface. In optical tweezers, focused laser beams can trap and manipulate microscopic particles by balancing radiation pressure forces with optical gradients. Even in biological systems, light-driven momentum transfer plays subtle roles, for instance in the tiny mechanical effects experienced by pigment molecules during photosynthesis. From a theoretical standpoint, this property arises naturally in quantum electrodynamics, QED, and quantum field theory, QFT. In these frameworks, photons are the carriers of the electromagnetic force, and their ability to exert momentum follows from the conservation laws that govern all physical interactions. Energy and momentum are conserved quantities. When a photon is absorbed by an atom, the atom's internal energy increases while its momentum changes to balance that of the absorbed photon. Similarly, when light reflects off a mirror, the momentum of the photons reverses direction, doubling the momentum transfer to the mirror in the process. Every such interaction obeys these strict conservation principles. It's also worth noting that radiation pressure can vary depending on the light's polarization and intensity. Circularly polarized light, for instance, can impart angular momentum as well as linear momentum, causing microscopic particles to spin. This angular momentum transfer is exploited in precision measurements, nanotechnology, and optical manipulation techniques. The interplay between linear and angular momentum in photons deepens our understanding of how light interacts with matter, not just energetically but mechanically. Despite their lack of mass, photons' ability to carry momentum illustrates one of the most profound lessons of relativity and quantum physics. Mass is not the sole carrier of physical influence. Energy itself, whether stored in fields, waves, or quanta, possesses the capacity to move, push, and exert force. Light, therefore, is not a passive phenomenon. It is an active agent capable of shaping matter, driving dynamics, and even influencing the structure of galaxies. The reality that something weightless can exert pressure overturns our classical expectations, but fits perfectly within the relativistic framework, where momentum is tied not to mass alone, but to energy and propagation through space-time. Light's pressure, though often imperceptible on human scales, governs cosmic processes, from the formation of planetary disks to the evaporation of comets as they approach the Sun. In this way, The photon's ability to carry momentum stands as another reminder of the profound unity between energy, motion, and the structure of the universe. A photon may have no rest mass, no size, and no internal structure, yet it can push, pull, and propel matter across the cosmos. Each beam of light, no matter how gentle, carries the power to move the universe itself, one quantum impulse at a time. The fact that photons have no rest mass is one of their most defining and fascinating characteristics. It may sound paradoxical that something can have energy, momentum, and observable effects, yet possess no mass whatsoever. But this property is not a flaw in our understanding. It is a profound revelation about how the universe fundamentally works. To comprehend it, we must explore the relationship between energy, mass, and motion through the lens of Einstein's theory of relativity, which redefined the way physics connects these seemingly distinct quantities. In classical Newtonian physics, momentum and energy are tightly linked to mass. A stationary object's momentum is zero, and its energy depends solely on its mass. Light, however, defies these intuitions. It travels at the speed of light c and cannot exist in any other state of motion. It is always moving. The concept of rest mass simply doesn't apply to photons because there is no frame of reference in which a photon is at rest. Unlike an electron or a baseball, you cannot catch up to a photon and see it standing still. In every possible inertial frame, a photon moves at exactly the same universal speed, c, roughly 299,792,458 meters per second. This constancy is what makes light, and by extension all massless particles, so unique. To understand why this is possible, we turn to the relativistic energy-momentum relationship. E squared equals pc squared plus m0c squared squared. Here, E is the total energy of a particle, p is its momentum, m0 is its rest mass, and c is the speed of light. For particles that have mass, both terms contribute to the total energy. But for a photon, the rest mass term is zero, m0 equals 0, simplifying the equation to E equals pc. This shows that the photon's energy is entirely due to its momentum and motion. It has no energy from mass itself. Yet this doesn't mean it lacks physical impact. Because energy and momentum are conserved quantities in nature, photons can still exert forces, transfer energy, and even change the motion of objects when they interact, as we've seen with radiation pressure. The idea of a massless yet energetic particle might seem strange, but it arises naturally from the structure of quantum field theory and special relativity. In relativity, mass is not synonymous with energy. It is one way, but not the only way that energy can manifest. Mass is a form of stored energy that an object possesses even when stationary, while photons represent pure kinetic energy, energy that can never be at rest. Their existence at the speed of light is not a choice, it is a requirement of their massless nature. If a photon were to have even the smallest amount of rest mass, it could not travel at c, and the entire framework of electromagnetism and relativity would collapse. Because photons are always in motion, their energy is defined by their frequency, as given by Planck's relation E equals h nu, where h is Planck's constant and nu is the frequency of oscillation. Their momentum likewise is given by P equals E divided by C equals h divided by lambda, where lambda is the wavelength. These relationships show that the properties we associate with movement in classical objects are encoded in photons through their frequency and wavelength, rather than through mass. In a sense, the oscillation of the electromagnetic field replaces the role that mass plays in other forms of energy. This property of being massless is what allows photons to travel at the ultimate cosmic speed limit. In relativity, only massless particles can reach, and must always move at the speed of light. Any object with mass requires infinite energy to accelerate to c, making such motion physically impossible. But photons, having no rest mass, exist perpetually at this limit, zipping through the universe as the fastest messengers of energy and information. Their constancy underpins much of modern physics. It is the reason why the speed of light is the same for all observers, no matter how they move, and why it serves as the fundamental constant linking space and time in Einstein's equations. The masslessness of photons also has profound implications for the range and nature of the electromagnetic force. In quantum field theory, the force carriers, called gauge bosons, can be massless or massive depending on the type of interaction they mediate. Because the photon is massless, the electromagnetic force has infinite range. Its effects can extend across the universe. If photons had even a tiny mass, electromagnetism would behave differently. Electric fields would decay exponentially over distance. Light would not travel indefinitely through space, and the structure of atoms and molecules would be fundamentally altered. Countless experiments have tested this, searching for any trace of photon mass, but every result to date confirms that its rest mass is exactly zero, within extremely tight limits. The absence of rest mass does not make photons any less real or tangible. On the contrary, it allows them to carry energy in the most efficient possible form. When photons interact with matter, their energy can manifest in various ways: heating a surface, ejecting electrons, generating electricity in solar panels, or even driving chemical reactions like photosynthesis. In all these cases, the photon's lack of mass is not a handicap, it's what enables it to act as a perfect courier of energy across any distance. We also see the implications of photon masslessness in astrophysics and cosmology. Because photons travel at sea, they serve as time capsules carrying information from the distant past. The light from galaxies billions of light years away brings us direct evidence of the universe's early history, encoded in the cosmic microwave background radiation. If photons had mass, their speed would depend on their energy, and light of different frequencies would arrive at different times, smearing out astronomical signals. Yet observations consistently show that light of all frequencies travels at the same speed through the vacuum, confirming the photon's massless perfection. It's important to distinguish between rest mass and relativistic mass, a term sometimes used to describe the energy equivalent of motion. Although photons have no rest mass, they possess energy and momentum, and thus they can influence massive objects gravitationally. According to Einstein's general theory of relativity, gravity does not act solely on mass, but on energy and momentum as well. This is why light bends around massive bodies like stars or black holes, a phenomenon known as gravitational lensing. The curvature of space-time affects photons' paths, even though they have no mass in the traditional sense. Their energy and momentum feel the geometry of space-time just as massive particles do. This leads to a deeper realization. Mass is not a prerequisite for having influence. Energy is the more fundamental quantity, and photons are pure packets of energy in motion. They carry momentum, they exert pressure, and they shape the universe through radiation and electromagnetic interaction, all without possessing mass. Their masslessness is precisely what makes them ideal messengers of nature's most fundamental forces and information. In short, photons have no rest mass because they cannot exist without motion. They are not static entities that can be stopped, weighed, or isolated. They are perpetual travelers, ripples of energy that only exist in transit. Their existence demonstrates the unity of energy, motion, and relativity, where even a massless particle can carry momentum, impart force, and reveal the structure of the cosmos. The photon's lack of rest mass is not a limitation but an essential feature that allows light to traverse the universe unimpeded, connecting stars, galaxies, and even the atoms in our eyes through the ceaseless flow of energy. The speed of light is one of the most fundamental and awe-inspiring constants in the universe. Because photons have no rest mass, they are bound by the laws of nature to travel at a single unchanging speed when moving through a perfect vacuum. This speed, known universally as the speed of light, is approximately 300,000 kilometers per second, or about 1 billion kilometers every hour. It is not just fast, it is the fastest that anything in the universe can possibly move. More profoundly, it is the very speed that defines the structure of space and time themselves. In the early 20th century, Albert Einstein revealed that the speed of light is not just a feature of electromagnetic radiation. It is the cosmic speed limit woven into the fabric of reality. Nothing with mass can ever reach this speed, because doing so would require infinite energy. Only particles that have no rest mass, like photons, can travel at this universal velocity. For them, it isn't an option or a choice, it is a built-in condition of their existence. A photon cannot move slower than light speed, nor can it ever stop. Its very nature compels it to move at this constant rate, which is the maximum possible speed for the transmission of information, energy, and causality in the universe. To understand why, consider what it means for something to have no rest mass. Massive particles like electrons, protons, or planets can exist at rest, possessing energy even when stationary. To accelerate them closer and closer to the speed of light, one must supply ever-increasing amounts of energy. The closer they get, the more energy is required, until reaching the speed of light would demand an infinite amount, which is physically impossible. Photons, however, start from the other side of that equation. Because they have no mass, they cannot slow down or exist in a state of rest. They are by definition always moving at the speed of light. Their energy and momentum come entirely from their motion, not from any inherent mass. This universal speed has deep implications and means that light travels through the vacuum of space with absolute consistency, unaffected by the speed or direction of its source. Whether emitted from a stationary lamp, a speeding spaceship, or a distant star moving through a galaxy, every photon in a vacuum moves at exactly the same speed. This remarkable property underlies Einstein's theory of relativity, which showed that time and space themselves must adjust to preserve the constancy of light's velocity. When an observer moves faster relative to a beam of light, time slows down and distances contract in such a way that the speed of light remains the same for everyone. It is this relationship that binds together the geometry of the cosmos and gives rise to the concept of space-time. The constancy of light speed also serves as the foundation for nearly every aspect of modern physics. It sets the scale at which cause and effect operate, the universal speed limit for how quickly any signal, particle, or influence can propagate. Nothing, not even gravity, can transmit information faster than this speed. It defines what we mean by simultaneity, shaping how we perceive time across the universe. For instance, when we look at a distant star, we are not seeing it as it exists now, but as it appeared when its light first left, perhaps millions or billions of years ago. In this sense, photons are messengers from the past, carrying ancient information across the cosmos at their unwavering speed. Yet while photons always travel at the same speed in a vacuum, they can appear to move more slowly when passing through materials such as water, glass, or air. This is not because the photons themselves are slowing down in the traditional sense, but because they are being repeatedly absorbed and re-emitted, or delayed, as they interact with the atoms in the material. The net effect makes the light seem to travel more slowly, but the moment a photon emerges from the medium and returns to the vacuum, it resumes its natural unchanging speed. This distinction is crucial to understanding why light bends when entering different substances, a phenomenon known as refraction, and why lenses and prisms can shape and separate beams of light without altering the fundamental nature of the photons themselves. The universality of light's speed also defines the maximum reach of human observation. Because photons move at this fixed rate, there is a limit to how far we can see into the universe. The most distant galaxies visible to our telescopes are those whose light has had enough time to reach us since the universe began. Beyond that boundary, often called the observable universe, light has not yet had enough time to traverse the cosmic distance, meaning those regions remain forever hidden from view. Thus, the speed of light is not only a constant of motion, but also a boundary of knowledge, setting the horizon of what can be observed and understood. Even in the realm of advanced cosmology, where space-time itself can expand faster than light, photons still obey this cosmic speed limit locally. They always move through the space they occupy at the same invariant rate, even though the space between distant galaxies can stretch and carry them apart faster than light can travel across that distance. This subtlety underscores that the speed of light is not merely about how fast light moves, but about how space-time itself behaves, a fixed measure built into the very geometry of the universe. In practical terms, the photon's unwavering speed is the cornerstone of countless technologies and systems we rely on daily. From GPS satellites that depend on relativistic corrections to maintain timing accuracy, to fiber optic communication networks that transmit information across continents, the constancy of light speed ensures that modern civilization functions with precision. It defines the limits of how quickly we can send signals, synchronize clocks, or even explore distant stars. Ultimately, the fact that photons travel at a universal speed is not just a numerical fact. It is a profound statement about the nature of reality. It tells us that the structure of the universe is built around a single invariant measure of motion, one that ties together time, space, energy, and causality into a unified whole. The speed of light is not merely how fast light travels, it is the heartbeat of the cosmos, the rhythm by which all events in space-time are measured. Photons, in their ceaseless motion, remind us that the universe is not static but dynamic, an ever-unfolding interplay of energy and geometry. They are the perfect embodiment of the principle that motion and energy can exist without mass, and through their unchanging speed, they reveal the deep unity between the physical and the geometric fabric of existence. In popular explanations, photons are often described as packets of energy, tiny bundles of light that travel through space like microscopic bullets. While this image helps convey the idea that light's energy comes in discrete quantized amounts, it is ultimately a simplification, a useful one for teaching or visualization, but one that hides the profound and counterintuitive reality of how photons actually behave. Photons are not little balls of light zipping along with definite edges or trajectories. They are quantum entities, and their nature cannot be fully captured by any analogy drawn from the familiar classical world. The packet of energy analogy originates from Max Planck's and Albert Einstein's discoveries in the early 1900s, when they showed that electromagnetic energy is emitted or absorbed in discrete quanta rather than in a smooth continuous flow. Describing photons as packets made sense then. It provided a bridge between the continuous waves of classical electromagnetism and the discrete energy exchanges observed in experiments like the photoelectric effect. But as quantum mechanics developed, scientists discovered that photons behave in ways that defy any picture based purely on ordinary experience. One major limitation of the packet analogy is that it suggests photons are localized, solid-like objects moving through space. In reality, a photon's presence is spread out. It does not exist in a single, sharply defined place until it interacts with something, such as an atom or a detector. Before that moment, it is better described as a probability wave, a field of potential outcomes indicating where and how it might be detected. When we perform an experiment, this wave collapses into a single event, a photon striking one point on a screen, for instance. But the probability distribution before that detection governs how the interference and diffraction patterns emerge, revealing that light behaves as an extended, delocalized quantum entity, not a compact flying particle. Consider the double-slit experiment, a cornerstone of modern physics. When a beam of light passes through two narrow slits and strikes a detection screen, it forms a pattern of bright and dark bands, an unmistakable sign of interference. Even when photons are sent one at a time over long periods, the interference pattern gradually appears. Each photon seems to interfere with itself, as though it had travelled through both slits simultaneously. No classical particle behaves this way. It is a manifestation of the photon's wave-particle duality. a principle that can be described mathematically but resists visualization in familiar terms. Another misconception from the packet analogy is that the photons move through space as self-contained clumps of energy. In truth, photons are excitations of the electromagnetic field, meaning they are inseparable from the field that gives them existence. They do not move through the field as marbles roll across a table. Rather, they are ripples within the field itself. Their energy is not contained inside them the way a battery contains electrical energy. It is expressed through their frequency and oscillation. When a photon is absorbed, it doesn't release some stored internal energy. Instead, it ceases to exist as the field transfers that quantized energy to another system, like an atom's electron. The packet image also fails to capture how photons interact, or rather, how they barely interact with each other. In ordinary matter, particles like electrons or atoms can collide and influence one another directly. Photons, however, generally pass through one another completely unaffected, even when they cross paths in the same region of space. Only under extreme conditions, such as in high-energy collisions near neutron stars or particle accelerators, can photons indirectly interact via quantum effects. This rarity underscores that photons are not tangible objects in the conventional sense, but mathematical excitations governed by the rules of quantum electrodynamics. Even the concept of a photon's path is foreign to classical thinking. When we trace the trajectory of a baseball, we can say with certainty where it is at every moment. For a photon, this is impossible. Between emission and detection, it doesn't follow a single path through space. Instead, it exists as a superposition of all possible paths, each contributing to the probability of where it might be found. Richard Feynman's path integral formulation of quantum mechanics captures this elegantly. To predict a photon's behavior, one must consider every conceivable route it could take and sum over them all. The photon does not choose a path until an observation forces a specific outcome, a concept that defies any classical analogy. This non-classical behavior extends to how photons store and carry energy. In classical terms, energy is often thought of as something that can be divided or diluted, like pouring water from a pitcher. But a photon's energy cannot be split into fractions. It is quantized. A photon with a certain frequency has a fixed energy, and that energy cannot be subdivided. If an atom lacks the right amount of energy difference between its levels to absorb that photon, the photon simply passes by. This discrete, all-or-nothing interaction distinguishes quantum energy transfer from the continuous energy exchange of classical waves. The packet of energy analogy also implies that photons might be countable in a way similar to tangible particles. Yet even this is subtly misleading. When dealing with very faint light, say just a few photons at a time, the number of photons can be determined statistically, but not always individually. In some quantum states of light, such as coherent states in a laser beam, the number of photons is not fixed but follows a probability distribution. The light behaves collectively as a single quantum field configuration, not as a simple collection of independent packets. This is why concepts like photon bunching and entanglement appear, phenomena that cannot be understood if photons were merely tiny separate pellets of light. Even the word photon can be deceptive if taken too literally. In popular culture, it conjures the image of a physical particle that we might capture, hold, or watch zoom through space. But in truth, a photon is not something that exists continuously in time in the way an ordinary object does. It is a quantum event, an interaction between fields. A photon is born when energy transitions from one state to another. It travels as a probabilistic field excitation, and it dies when that energy is absorbed. Between those points, it is not an object with persistent existence, but a quantum relationship between emission and absorption events. To make sense of this strange reality, physicists often rely on analogies to bridge the gap between human intuition and the quantum world. But every analogy, whether calling photons packets, waves, or particles, captures only part of the truth. Each metaphor is like a shadow of a higher dimensional concept that can only be fully described by mathematics. In the quantum domain, the behavior of photons is governed not by fixed trajectories or continuous energies, but by probabilities and quantization. Their existence is not absolute but relational, defined by how they interact with matter and observers. Thus, while describing photons as packets of energy is a helpful shorthand, it's crucial to remember that it's a conceptual scaffold, not a literal picture. The true nature of photons lies beyond classical imagination. They are neither objects nor waves in the familiar sense, but manifestations of the quantum field's discrete probabilistic character. They behave according to principles that challenge every intuitive notion we have about motion, substance, and even existence itself. In this way, photons remind us that the universe's deepest workings are not built from simple analogies, but from elegant abstractions. Their behavior invites us to think beyond the everyday, to embrace a reality where the boundaries between waves and particles, energy and matter, motion and information all blur into the seamless unity of quantum physics. At the heart of understanding light, and indeed understanding photons themselves, lies the concept of the electromagnetic field. This field is one of the most fundamental structures in the universe, an invisible, continuous entity that fills all of space. Every beam of light, every magnetic force, every spark of electricity arises as a manifestation of this vast field. It is not confined to wires, magnets, or visible rays. It is everywhere, woven into the very fabric of reality. And photons, those elusive quanta of light, are nothing more or less than tiny quantized excitations, momentary ripples in this universal field that carry energy, momentum, and information across the cosmos. To appreciate this, it helps to remember that before quantum theory, physicists viewed the electromagnetic field as entirely smooth and continuous. James Clerk Maxwell's equations, formulated in the 19th century, described how electric and magnetic fields oscillate together, generating waves that travel through space at the speed of light. These equations unified electricity, magnetism, and light into a single framework, revealing that visible light is simply one small part of a vast electromagnetic spectrum that includes radio waves, microwaves, X-rays, and more. This classical picture was elegant and powerful, but it could not explain why light sometimes behaves as if it were made of discrete particles, or why energy is transferred in fixed amounts rather than continuously. Quantum mechanics, and later quantum field theory, brought the missing insight. The electromagnetic field is indeed continuous, but it is not infinitely divisible in how it carries energy. It can only oscillate or change in discrete steps, or quanta. These quanta are the photons. In this sense, photons are not separate entities moving through space. They are the smallest possible packets of disturbance in the electromagnetic field itself. When a photon is emitted, the field shifts from one quantized energy state to another. When it is absorbed, that shift reverses. The field is the underlying reality. Photons are the fleeting ripples that appear when it vibrates in quantized ways. Imagine dropping a pebble into a still pond. The ripples that spread outward are not objects distinct from the water. They are the motion of the water itself. Similarly, when an atom emits a photon, it's as if a ripple has been created in the electromagnetic field. That ripple travels outward through the vacuum of space until it interacts with something else, perhaps another atom which absorbs it, or a detector that registers its arrival. Unlike the pond analogy, though, the electromagnetic field's ripples are quantized. There is no such thing as half a photon, or a photon with arbitrary energy. The energy of each ripple is precisely determined by the frequency of its oscillation, a principle that links directly back to the relation between energy and frequency that governs all electromagnetic radiation. This quantum view transforms the way we think about space and light. The electromagnetic field is not a backdrop or a medium through which light travels, it is what light is made of. Even in regions of space that appear empty, the field is still there, humming with potential activity. It can be excited into photons at any time when energy is exchanged, and even when no real photons are present, it fluctuates subtly due to quantum uncertainty. These fluctuations, known as zero-point energy, give rise to remarkable phenomena such as the Casimir effect, where two uncharged metal plates placed close together experience a tiny attractive force caused by the field's vacuum fluctuations. The field's omnipresence also explains why light can propagate across the universe without any medium like air or ether. The electromagnetic field does not need anything external to support its waves. It exists everywhere, self-sustaining through the interplay of electric and magnetic components that perpetually regenerate each other. A disturbance in the field, a photon, can thus travel through the vacuum effortlessly, carrying energy across billions of light years. This is how the light from distant galaxies, emitted eons ago, still reaches our telescopes today, crossing the silent expanses of space with unerring precision. Moreover, the electromagnetic field doesn't just transmit energy, it also governs how charged particles interact. Electrons and protons, for instance, communicate through the exchange of virtual photons, the invisible intermediaries that convey the electromagnetic force. These virtual photons are constantly being created and annihilated within the field, mediating every attraction and repulsion we observe between charges. Though they cannot be directly detected, their effects are measurable, forming the backbone of all electromagnetic interactions from the smallest atoms to the largest cosmic structures. This interplay between the continuous field and its discrete excitations also underpins the wave-particle duality of light. When we observe light spreading out, bending, or interfering, we are witnessing the field's wave-like behavior, but when we detect individual photons, we are observing its quantized particle-like nature. These two aspects are not separate phenomena, but complementary views of the same underlying process, the electromagnetic field behaving in quantized, probabilistic ways. The power of this field-centered view becomes evident when we realize that photons are not merely confined to visible light. Every part of the electromagnetic spectrum corresponds to photons of different frequencies and energies, from long wavelength radio photons to ultra-energetic gamma photons. Each of these is a particular kind of excitation in the same universal field, differing only in how rapidly it oscillates and how much energy each quantum carries. This continuity unites all forms of electromagnetic radiation under a single, elegant framework. Because the electromagnetic field fills all of space, it also means that photons can interact with it in subtle and complex ways. They can be absorbed, scattered, or redirected by other fields and particles. For example, when light passes through glass or water, the electromagnetic field interacts with the charged particles inside the material, causing the light to bend and slow in apparent speed. These effects, though seemingly classical, emerge from the quantum interactions between photons and the electromagnetic field's excitations within matter. At the deepest level, this picture tells us that space itself is never truly empty. Even in the most perfect vacuum, the electromagnetic field is always present, fluctuating, vibrating, and capable of giving rise to photons. When light crosses the cosmos, it is not moving through something. It is the electromagnetic field itself, expressing motion, transmitting energy and information across the void. Every sunrise, every reflection, every signal travelling through fibre optic cables is the electromagnetic field in action, vibrating, quantizing, and connecting distant parts of the universe through its excitations. Thus, photons are not foreign objects inhabiting the electromagnetic field. They are its purest expressions, the smallest building blocks of light and electromagnetism alike. They are the field's voice, the quantized ripples that translate energy into motion and connect matter across infinite space. In them, we glimpse the unity between the discrete and the continuous, between matter and energy, between the visible and the unseen. And as we look deeper into the workings of this field, we begin to see that the photon is not unique in this way. Many other fundamental forces also arise from their own fields and corresponding excitations, a realization that leads us naturally to the next step in our understanding. Just as photons serve as the quanta of the electromagnetic field, other fundamental forces in nature also have their own corresponding carrier particles, each one a messenger that transmits interactions between matter in the quantum realm. In the grand framework of quantum field theory, every force arises from the exchange of such particles known as gauge bosons. The photon, elegant and massless, is one member of this distinguished family of force carriers. Understanding its place among them helps reveal both the unity and diversity of the fundamental forces shaping the universe. The photon mediates the electromagnetic force, one of the four fundamental forces of nature. This force governs the behavior of all charged particles, from the electrons orbiting atomic nuclei to the electromagnetic waves spanning the cosmos. Whenever two charged particles interact, whether they attract or repel each other, they do so through the exchange of photons. These interactions are described by the theory of quantum electrodynamics, or QED, which remains one of the most precisely verified theories in all of science. In QED, photons are the silent intermediaries, continuously exchanged between particles, even in empty space, giving rise to the electric and magnetic forces we observe. But the photon's role becomes even more fascinating when compared with its counterparts in the other fundamental interaction. In the realm of the strong nuclear force, for example, the carriers are called gluons. These particles bind quarks together inside protons, neutrons, and other hadrons. Like photons, gluons are massless, but they differ in one crucial way. Photons do not carry the charge they mediate, while gluons do. Photons can interact with charged particles but not with one another under normal conditions. Gluons, on the other hand, carry what is known as color charge, meaning they interact not only with quarks but also with each other. This property gives the strong force its extraordinary strength and confinement, the reason why quarks can never be isolated individually. Then there are the W and Z bosons, the carriers of the weak nuclear force, which governs processes such as radioactive decay and the nuclear reactions that power stars. Unlike photons or gluons, these particles are massive, and their mass dramatically limits the range of the force they transmit, while the electromagnetic force has infinite reach. The weak force acts only over subatomic distances within the heart of atoms. The large mass of the W and Z bosons, tens of thousands of times that of an electron, is what makes weak interactions so short-ranged and rare in comparison to the omnipresent electromagnetic effects mediated by photons. The final member of this set of forces is gravity, which, according to our current understanding, would be mediated by a hypothetical particle called the graviton. If it exists, the graviton would share one key property with the photon. It would be massless, allowing gravity to act over infinite distances, just like light. However, unlike photons, gravitons have not yet been detected. Gravity remains described best by Einstein's general theory of relativity, which interprets it not as a force transmitted by particles, but as the curvature of space-time itself. Still, if a quantum theory of gravity is someday developed, it is likely to parallel the photon's role as the quantum of the gravitational field. By comparing these force carriers, we see how nature's interactions differ mainly in two fundamental aspects: the mass of the mediating particle and whether or not it carries its own charge. The photon's masslessness makes the electromagnetic force infinite in range, allowing light to travel unimpeded across billions of light years and making magnetism and electricity pervasive throughout the universe. Its neutrality ensures that photons do not interact with one another in ordinary conditions, preserving the linear and predictable nature of electromagnetic phenomena. In contrast, the gluon's self-interacting nature confines them within atomic nuclei, while the massive W and Z bosons confine their effects to the subatomic scale. The unity among these particles becomes clearer under the framework of the standard model of particle physics, which treats them all as gauge bosons arising from symmetries of their respective fields. The photon in particular emerges from the unification of the electromagnetic and weak forces, a synthesis known as the electroweak theory. According to this theory, at extremely high energies, such as those that existed moments after the Big Bang, the electromagnetic and weak interactions were indistinguishable. Only as the universe cooled did they separate into two distinct forces, with the photon remaining massless while the W and Z bosons gained mass through their interaction with the Higgs field. This elegant unification reveals that the photon is not an isolated phenomenon, but part of a broader cosmic symmetry connecting multiple fundamental interactions. The photon's role as a force carrier also extends beyond the microscopic world to influence structures on cosmic scales. Every electromagnetic process, from the glow of stars and the dynamics of galaxies to the operation of modern technology, is governed by the exchange of photons. They mediate not only visible light but also radio waves, microwaves, infrared radiation, X-rays and gamma rays, all manifestations of the same electromagnetic interaction. Their infinite range and capacity to carry energy and momentum make photons the universal messengers of the cosmos, bridging atomic and astronomical realms alike. In many ways, the photon stands as a symbol of balance among the fundamental forces. It is the simplest of the gauge bosons, massless, chargeless, and remarkably stable, yet its effects dominate much of the observable universe. Through it, we perceive nearly all that we know: the light from distant galaxies, the warmth of the sun, the information transmitted across fiber optic networks, and the structure of atoms themselves. Every photon that reaches our eyes or instruments carries with it the imprint of an interaction that once occurred somewhere in the vast electromagnetic web of reality. By seeing the photon in this context, we recognize that it's part of a much grander system of relationships. The same fundamental principles that describe how photons mediate electromagnetism also govern the gluons, W and Z bosons, and possibly the graviton. All are expressions of a deeper symmetry underlying the forces of nature. And while the photon may appear the most familiar of these carriers, it is also the most revealing, for through its behavior we glimpse how energy, force, and field intertwine to create the dynamic structure of the universe itself. From here, it becomes natural to explore not only how photons mediate forces, but also what unique intrinsic properties they possess, characteristics such as spin and polarization, which determine how they interact with matter and with each other in the quantum world. Every photon carries with it an intrinsic property known as spin, a subtle but fundamental aspect of its identity that distinguishes it from other types of particles. Spin is not spin in the everyday sense. It's not as if a photon is literally rotating around an axis like a tiny ball. Rather, spin is a form of intrinsic angular momentum that arises from the mathematical structure of the photon's quantum field. It is a quantum mechanical property that reflects how the photon's electromagnetic field oscillates as it moves through space, and it is central to understanding how light interacts with matter, how it can be polarized, and even how it can carry information. For photons, this intrinsic spin always has a magnitude of 1 unit in the quantum mechanical scale of angular momentum, but because photons have no rest mass, they can only exhibit 2 spin orientations, often referred to as spin up and spin down, or more precisely right-handed and left-handed helicities. These correspond to the 2 possible directions in which the electric and magnetic fields of the photon can rotate as the photon travels forward. In simpler terms, imagine the oscillating electric and magnetic fields of a photon forming a kind of twisting or spiraling pattern as the photon moves. This rotational character is what we recognize as the photon's spin state. This rotational nature gives rise to one of the most important and observable properties of light: polarization. Polarization describes the orientation of the electric field oscillations in a light wave. When light is linearly polarized, its electric field oscillates in a fixed plane, such as vertically or horizontally. When light is circularly polarized, the electric field rotates in a helical pattern as it travels, corresponding to one of the photon's 2 spin helicities, right-handed or left-handed. And when the field rotates in an irregular or mixed way, the light is elliptically or partially polarized. Unpolarized light, such as that from the sun or a common lamp, consists of photons with all possible spin orientations randomly mixed together, leading to no fixed polarization direction. The phenomenon of polarization is not just a theoretical curiosity, it has profound practical and physical significance. It determines how light interacts with materials, surfaces, and even biological structures. For example, certain materials known as polarizers allow only photons with a particular polarization direction to pass through, blocking others. This is the principle behind polarized sunglasses, which filter out horizontally polarized glare reflected from water or roads, while allowing vertically polarized light to reach the eye. Similarly, in liquid crystal displays, LCDs, polarization control allows light to be selectively transmitted or blocked at the pixel level, forming images with precision. At a deeper level, polarization reveals how the photon's spin interacts with the microscopic world. When light encounters atoms or molecules, its polarization can influence how energy is absorbed or emitted. In some materials, polarized light can even change its orientation upon reflection or transmission, a phenomenon known as birefringence, which occurs because the medium responds differently to different polarization states. In more advanced settings, such as quantum optics, controlling the polarization of individual photons allows scientists to encode information, manipulate quantum bits, qubits, and perform secure quantum communication, technologies that rest directly on the photon's spin structure. Spin also distinguishes photons from other types of particles in the quantum universe. In the standard model of particle physics, particles are categorized based on their spin into two broad families, fermions and bosons. Fermions, such as electrons, protons, and quarks, have half-integer spins, like 1/2 or 3/2, and obey the Pauli exclusion principle, which prevents them from occupying the same quantum state. Bosons, on the other hand, including photons, gluons, and W and Z bosons, have integer spins, like 0, 1, or 2, and are not subject to that exclusion. Instead, they can share identical quantum states, allowing them to form coherent ensembles. This property is what enables phenomena like laser light, where countless photons exist in perfect synchronization, sharing the same phase, frequency, and polarization. The photon's spin of 1, combined with its lack of rest mass, also dictates how it propagates. Unlike massive particles, photons can have only 2 spin states instead of 3. Massive spin 1 particles, like the W and Z bosons, can have spin pointing in any of 3 directions, up, down, or aligned with their direction of motion. But for the photon, which must always travel at the speed of light, the spin component along its direction of motion, called the longitudinal component, is forbidden. Only the 2 transverse spin states remain, right-handed and left-handed helicities, corresponding precisely to the 2 possible circular polarization states of light. This restriction is not a limitation. It's a natural consequence of the deep symmetries in the laws of electromagnetism and relativity. Polarization can also reveal intricate details about the world around us. In astrophysics, the polarization of light from distant stars and galaxies carries clues about cosmic magnetic fields and interstellar dust. The cosmic microwave background radiation, the afterglow of the Big Bang, is partially polarized, a feature that encodes information about the early universe's structure and even gravitational waves that may have rippled through space-time shortly after the universe's birth. Similarly, in materials science, polarized light microscopy allows scientists to study the internal structure of crystals, fibers, and biological tissues by examining how polarization changes upon interaction. Even in the quantum realm, the photon's spin and polarization are inseparable from its identity. A photon's polarization can become entangled with another photon's, meaning their polarization states become linked across space, such that measuring one instantly determines the state of the other. This phenomenon, experimentally verified countless times, lies at the heart of quantum entanglement, quantum teleportation, and quantum encryption. Here again, the photon's spin serves as both the physical property being manipulated and the channel through which quantum information flows. In all these contexts, the spin and polarization of photons bridge the microscopic and macroscopic worlds. They embody the unity of the photon's dual nature, quantum and wave-like, abstract and yet tangible. Through polarization, the invisible spin of the photon becomes something we can observe, measure, and harness. It governs the colours we see in the sky, the way reflections shimmer on water, the images that appear on screens, and the communication systems that form the backbone of modern technology. Thus, the photon's spin is far more than an abstract number. It is the foundation of light's behaviour, the hidden rhythm that gives every beam of light its orientation, structure, and power to interact with matter. It reminds us that even the simplest quantum of energy, the photon, carries with it a complexity that connects the geometry of space, the symmetry of fields, and the patterns of information that pervade the universe. And while photons often act as silent messengers, transmitting energy and force without mutual interference, there are rare circumstances, extreme and fascinating, where they can subtly interact with one another, revealing yet another layer of their mysterious nature. Under ordinary conditions, photons appear to pass through one another completely unaffected, like ghosts drifting through the same space without ever colliding. Shine two flashlights so that their beams cross, and you'll notice nothing unusual. The light continues in straight lines as though the other beam were not even there. This remarkable behaviour reflects a key property of the photon. It does not easily interact with other photons. In everyday environments, light does not scatter off light. Yet in the deeper framework of quantum electrodynamics, QED, the quantum field theory that governs how light and matter interact, there are rare and subtle circumstances under which photons can influence each other. These are among the most delicate and fascinating effects predicted by modern physics, lying at the very frontier of experimental detection. To understand why photons rarely interact, we must first recall what they are: excitations of the electromagnetic field. The photon carries no electric charge, and electromagnetic interactions are mediated by charge. Since photons themselves are neutral, they cannot directly exert electromagnetic forces on one another the way charged particles can. This is in stark contrast to the carriers of the strong nuclear force, the gluons, which interact intensely because they carry the very colour charge associated with that force. Photons, having no such charge, simply glide through one another's fields in silence. However, QED shows that this non-interaction is not absolute. The electromagnetic field does not exist in isolation. It is coupled to all charged particles, most notably electrons and positrons. In the quantum picture, the vacuum is not an empty void, but a restless sea of virtual particles flickering in and out of existence for unimaginably brief moments. These virtual electrons and positrons can momentarily pop into being, interact with photons, and then vanish again. During these fleeting moments, they can mediate an indirect interaction between two photons, a process known as light-by-light scattering. In essence, one photon can briefly generate a pair of virtual charged particles, which then interact with another photon before disappearing. This phenomenon is extraordinarily rare because it involves multiple layers of quantum fluctuation and requires very high energies to produce measurable effects. Nonetheless, it has been predicted by QED for decades and represents one of the most subtle consequences of the theory. At low energies, such as those found in ordinary light or even in the powerful lasers we use today, photon-photon interactions are so weak that they are effectively unobservable. The probability of two visible photons interacting in this way is vanishingly small, so small that a beam of sunlight could travel through a solid light beam of the same intensity for the entire lifetime of the universe without a single photon-photon collision. This non-interaction is precisely what makes light so stable and predictable at human scales, allowing beams to cross and interfere linearly without distortion. But at extreme energies, those found in high-energy physics experiments or astrophysical environments, the situation changes. When photons carry enough energy, their fields can distort the quantum vacuum, momentarily polarizing it and giving rise to detectable effects. In these conditions, virtual particle loops can alter the way light propagates, effectively allowing photons to scatter off each other or change their polarization through a process known as vacuum birefringence. This exotic effect has actually been observed in recent years at powerful particle accelerators such as CERN's Large Hadron Collider, LHC. In collisions between heavy ions, the surrounding electromagnetic fields are so intense that they generate enormous bursts of photons. When these photon clouds interact, a minute fraction of the photons scatter off one another, leaving detectable traces in the resulting particle patterns. These experiments have provided the first direct confirmation of photon-photon scattering, validating QED's predictions with extraordinary precision. Even more dramatic versions of these interactions are thought to occur naturally in extreme cosmic environments. Around magnetas, neutron stars with magnetic fields trillions of times stronger than Earth's, the quantum vacuum behaves differently from the empty space we're familiar with. In such conditions, the vacuum itself becomes polarized by the intense electromagnetic field, causing light to bend, split, or change polarization as it travels. This is a direct consequence of photon-photon interactions occurring through the mediation of virtual charged particles. Observations of polarized light from distant magnetaires provide compelling, though indirect, evidence that these quantum processes are shaping the behavior of light across vast cosmic distances. Another fascinating consequence of photon interactions predicted by QED is photon splitting, a process in which a single high-energy photon can, in the presence of a strong magnetic field, divide into two lower-energy photons. This phenomenon, while never observed directly in the laboratory due to the enormous field strengths required, is expected to occur near magnetas and other extreme astrophysical sites. In such places, light not only curves around gravity wells, but also transforms through interactions with the very fabric of the quantum vacuum. Photon-photon interactions also play a subtle role in modern particle physics. At extremely high energies, far beyond those accessible to visible light, photons can generate real matter, converting their energy into electron-positron pairs when they collide. This is the reverse of the process by which electrons and positrons annihilate into photons. Such pair production occurs naturally in environments like the cores of stars or during the intense gamma-ray bursts produced by collapsing supernovae. It beautifully illustrates Einstein's principle of mass-energy equivalence, showing that even light can create matter when concentrated enough. These rare interactions remind us that even something as seemingly simple as light contains hidden layers of complexity. On the surface, photons behave as independent messengers of energy, passing through one another without consequence. Yet beneath that calm simplicity lies a quantum world where the electromagnetic field constantly fluctuates, virtual particles flicker in and out of being, and photons whisper to each other through the fabric of space-time itself. The fact that these effects are so small and difficult to observe is not a weakness of the theory, it is a testament to the precision and subtlety of nature's design. In practical terms, photon-photon interactions have very little impact on everyday life, but their theoretical and experimental confirmation stands as one of the greatest triumphs of quantum electrodynamics. QED remains the most accurate theory ever constructed by humanity, with predictions verified to astonishing degrees of precision. The fact that it can account for something as delicate as light, scattering off light, and match experiment to within a few parts per billion, demonstrates both the depth of our understanding and the intricate structure underlying even the simplest phenomena. Through the lens of these rare interactions, photons reveal their dual nature once again. Most of the time, they behave as independent waves and particles, but at the extremes of energy, density, and magnetic intensity, their mutual influence becomes undeniable. In those moments, light ceases to be passive illumination and becomes an active participant in the dynamic interplay of forces shaping the quantum world itself. And as we reach the edge of what photons can do, it is fitting to step back and look at the bigger picture, to summarize how modern physics understands these elusive quanta of light and what they tell us about the nature of energy, matter, and reality itself. In our modern scientific understanding, the photon stands as one of the most fundamental entities in the universe, a particle so simple, so irreducible that it cannot be divided into smaller parts or explained in terms of anything more basic. It is not built from constituents, not composed of hidden structures, and not assembled from smaller particles or forces. Instead, each photon is a quantized excitation, a discrete vibration of the electromagnetic field that permeates all of space. Every photon, regardless of its origin or energy, is a direct expression of that field's quantum nature. This recognition that photons are not made of anything is one of the most profound achievements of modern physics. In the same way that an atom is the smallest unit of matter, that retains its chemical identity, a photon is the smallest possible unit of electromagnetic radiation. It cannot be split, weakened, or subdivided into fractions of itself. When a photon interacts with matter, it delivers its energy as a single quantum event, either transferring it entirely or not at all. There is no half photon, no smaller piece of light. This indivisibility defines the very essence of quantum physics, that the universe at its deepest level operates not through continuous flows, but through discrete, quantized exchanges of energy. Every photon is defined by three fundamental characteristics: its energy, its frequency, and its momentum, all of which are intimately connected. A photon's energy is determined by the rate at which the electromagnetic field oscillates, or its frequency. The higher the frequency, the greater the energy the photon carries. Its momentum, though subtle, reflects the direction and magnitude of that motion through space, and can exert real, measurable force when transferred to matter. These three properties, energy, frequency, and momentum, completely describe a photon's physical identity. There is no additional substance behind them, no hidden core or internal machinery. The photon simply is the field vibrating in quantized motion. This modern view emerged from the synthesis of quantum mechanics, relativity, and field theory, a framework known as quantum electrodynamics, QED. In QED, the electromagnetic field is treated as a continuous entity that can exist in different states of excitation. The photon corresponds to the smallest possible jump between those states, the minimal ripple that carries a quantum of energy from one place to another. It is both a particle and a wave, but more precisely it is a quantum of the field, behaving as a wave in propagation and as a particle during interaction. The familiar dichotomy of wave and particle dissolves in this view, replaced by a more complete description that unites them within a single formalism. One of the most elegant aspects of this understanding is its universality. Every photon, whether it belongs to visible light, infrared radiation, microwaves, radio waves, or gamma rays, is the same type of particle, the same kind of excitation, differing only in frequency and energy. A radio photon may be millions of times less energetic than a gamma ray photon, but both are governed by the same principles and equations. The entire electromagnetic spectrum is, therefore, a continuum of photon energies, spanning the most gentle ripples of long-wavelength radiation to the most energetic bursts of cosmic gamma rays. This continuity unifies all electromagnetic phenomena, from the light of a candle to the radiation from distant quasars, under a single quantum concept. Crucially, photons are massless. They have no rest mass, and this absence is not an oversight. It is essential to their nature. Because they have no rest mass, photons must always travel at the ultimate cosmic speed, the speed of light. They can never slow down, stop, or exist in a stationary state. Their existence is inseparable from motion. This constant velocity makes them the perfect carriers of energy and information, allowing them to traverse the universe unimpeded and to transmit electromagnetic forces across infinite distances. It also ensures that the electromagnetic force itself has an infinite range, connecting objects from the subatomic to the cosmological. Despite their simplicity, photons exhibit astonishing richness in behaviour. Their spin gives rise to polarization, which affects how light interacts with matter. Their momentum allows them to exert pressure, pushing on surfaces and particles. Their quantum properties enable phenomena such as interference, diffraction, and entanglement, effects that defy classical logic but align perfectly with quantum principles. Each of these manifestations arises not from internal complexity, but from the fundamental symmetries of the electromagnetic field itself. Moreover, photons play a role far greater than the illumination or visual perception. They are the fundamental messengers of the electromagnetic interaction, the glue that binds charged particles together and allows atoms and molecules to communicate across space. Every time an electron jumps between energy levels in an atom, it emits or absorbs a photon. Every radio transmission, every wireless signal, every ray of sunlight, every reflection or shadow you see is the result of photons in action. They are the universe's communicators, the quanta through which energy, force, and information flow. In the broader context of particle physics, the photon also occupies a position of exquisite symmetry and elegance. It is one of the gauge bosons, the mediators of nature's fundamental forces. Alongside gluons, which carry the strong nuclear force, and the W and Z bosons, which mediate the weak force, the photon represents one aspect of a unified framework describing all known interactions. The photon's simplicity, its lack of mass, charge, and self-interaction under normal conditions, makes it the purest example of a gauge boson, an unadulterated expression of a field's symmetry. When viewed through the lens of cosmology, the importance of photons becomes even more profound. The light that fills the universe, the cosmic microwave background radiation, is composed of ancient photons released nearly 14 billion years ago, when the universe first became transparent. These photons have been travelling ever since, carrying with them the imprints of the early cosmos. Every photon we detect from that primordial light is a direct messenger from the dawn of time, proving that photons are not transient curiosities but durable, enduring features of the universe's structure. Thus, in our modern view, photons are not made of anything smaller or simpler. They are elementary quanta, indivisible excitations that reveal the quantum nature of the electromagnetic field. Their properties are entirely defined by the fundamental constants of nature. Planck's constant, which sets their energy scale, the speed of light, which determines their motion, and the structure of the electromagnetic field, which gives them form. When we speak of photons, we are speaking of one of nature's most perfect creations, simple, fundamental, and yet infinitely expressive. They are the building blocks of light and the carriers of one of the four fundamental forces. Every spark, every star, every signal, and every sight we experience is a symphony of photons, countless quantized ripples of the electromagnetic field, weaving the universe together through their ceaseless motion. And as we reach the culmination of this exploration, one final realization becomes clear. Photons are not merely things within the universe, they are among the most basic expressions of the universe itself, encapsulating the seamless unity between matter, energy, and the quantum fabric of reality. Photons, in their essence, illuminate far more than the world around us. They illuminate the very foundations of reality itself. They are not made of anything in the conventional sense. They are pure manifestations of energy, the simplest excitations of the electromagnetic field, and among nature's most elementary building blocks. To ask what a photon is made of is therefore to miss the subtle beauty of what it truly represents, the point where matter and energy, continuity and discreteness, the visible and the invisible all meet in perfect harmony. In the grand architecture of the universe, photons occupy a singular role. They bridge the microscopic and the cosmic, the quantum and the classical. Every beam of sunlight, every glimmer from a distant star, every pulse of data in a fiber optic line is a procession of these field quanta, ferrying information across the fabric of space-time. They connect atoms within molecules, stars within galaxies, and ultimately human perception to the cosmos itself. When we see, when we measure, when we communicate, it is photons that make it all possible. And yet, for all their ubiquity, photons defy the categories our minds naturally seek. They are not particles in the traditional sense, nor waves in the classical one. They are both and neither. Quantum phenomena that reveal the limitations of human intuition. They are born in the transitions of atoms, live as ripples in the electromagnetic field, and die in the act of absorption. Their energy transferred wholly and instantly to another system. Between these moments, they do not exist as tangible things, but as probabilities, mathematical expressions of what might happen. The photon, then, is a messenger not only of light, but of quantum truth. It teaches us that nature's smallest scales are governed not by certainties, but by possibilities. That reality is not built from tiny solid objects, but from patterns of energy and interaction. To study photons is to peer into the quantum fabric of existence, where the laws of the universe are written not in matter, but in vibration, symmetry, and probability. This realization invites a kind of awe, the light that streams through the cosmos, that nourishes life and reveals beauty, is the same light that encodes the secrets of the quantum world. The photon is both symbol and substance of the unity between simplicity and complexity, a reminder that even the smallest quantum of energy embodies the universe's most profound elegance. In the end, to understand photons is to glimpse the strange perfection of nature's design. They are not composed of smaller parts because they do not need to be. They are the pure expression of the electromagnetic field's quantum nature, the universe's way of moving energy and information in its most elemental form. Through them, we see that light is not just something that travels through space. It is how the universe itself communicates, one quantum at a time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like this video and subscribe to the channel for more such amazing videos.